Good morning, Astronomy 1010. Welcome to part 2 of lecture 12, where we are summarizing how planetary atmospheres and terrestrial geology fuse together. I'm hoping this will be a gateway transition into learning about the solar system outside the asteroid belt, Jovian planets and their moons, which are actually a lot of fun. Today we're going to have our usual 1 hour and 15-minute lecture. And then we're going to do a fun, easy homework that is not the one currently listed. It's going to be a combination of problems from 9 and 10. Nice to see so many participants today after Monday. Nori, it's nice to see you back. And Kim, we missed you guys. We really did. Okay.
I was doing my graduation walk. That's why I wasn't here.
What happened, Kim?
I was doing my graduation walk.
No way. Congratulations. How's that feel?
Good, but I'll be coming back in the fall anyways.
Oh, okay. Well, at $500 a class, you can't beat it. It's $500 at CC. It's whatever, $1,200 at URI. It's $3,000 at Bryant, and it's $5,000 at Brown. So yeah. Take as many classes as you can here before moving on. It's good value for your money. At least I hope it is. In our last class, I kind of had a very technical lecture where we talked about gas particles, the Maxwell-Boltzmann distribution of velocities. Whoa, Austin, this is making up for all of your missed classes here. What's this little guy? Let's just have a moment.
This is Penny. She's a little psycho, but
Penny is hell. Is this a new dog, or did you have this whole time?
No, this is my cousin's dog. When I first moved to Providence, that was my dog.
Well, that dog is cute as a button. We want to see a whole lot more of Penny.
Okay.
And thank you for sharing. The animals really help the day go by. So we talked about a Maxwell-Boltzmann distribution of velocities, and basically the whole point of the lecture was atmospheres leak away into space, right? Atmospheres get lost. Today, let's think about topics I want to cover. I want to talk about a little bit about climate change and atmospheric circulation. I'd like to talk about fundamental planetary properties. In fact, while your attention is fresh, maybe we could start there. This is sort of the summation of what I should be doing at the end. But while our minds are fresh, I want you guys to think about this important takeaway. I'm just kind of making it up as I go here and having fun. If you think about planets, if you're interested in outer space and planets and whether there could be life on other worlds, then you want to start looking around for places where you could find life. Places like Mars, Jupiter's moon Europa, perhaps even Saturn's moon Enceladus or Titan. You start looking at what are qualities that planets have that allow them to develop into interesting worlds and not simply a beat up asteroid in space like the moon is. And it turns out that there's kind of three fundamental planetary properties. I probably should have done this at the end of today's lecture, but because it's one of the most important messages, I want to do it while we're fresh. The first fundamental planetary property is size. Let's see what you've learned during the course of these lectures. What role does size play in the evolution of a planet? Why does it matter that Earth has a 6,400 kilometer radius, but Mercury has a 2,400 kilometer radius?
Like the properties of the planet are affected by the size?
Yeah, well, I'm thinking of some important things in terms of planetary geology, maybe in terms of atmospheres. What does...
Like the density of the atmosphere? The gravity of everything?
We can talk about the density of the planet. The density of the atmosphere, well, the density of the atmosphere does matter too. You know, I'm thinking, without giving away the goose all at once, all planets are made from the same pancake batter. They all come from the Protozoan Nebula. And there were no video cameras 4.6 billion years ago, so I can't show you the Protozoan Nebula, but I can imagine with my weed smoking artist friends what it might have looked like, and it might have looked something like this. And this is a paste of hydrogen and helium gas with little bits of silicate rock and metal floating around in it. And Mercury and the moon and Earth were all made from a homogeneous mixture of this stuff, more or less. Yet they don't look anything like each other today. Earth is capable of supporting life. Mercury is clearly not. What role does size play in how a planet goes from a clump of this stuff to eventually looking like, this?
Wouldn't size affect in terms of, wouldn't it affect the geology of a planet? Because the bigger the planet, the longer it would take for the lithosphere to get closer to the core, which would result in more things happening like volcanism.
Ryan, I am conducting your little symphony here. That is beautiful. The simple way to put it is internal heat. Bigger planets hold more internal heat. And as Ryan mentions, internal heat keeps your lithosphere thin. It forms cracks. It forms vents where volcanoes can spew out atmospheric gas. Tectonic plates can move around. Internal heat also provides volcanism, which provides atmospheres. In terms of atmospheres, there's one other thing besides internal heat that size does for us. You've perfectly guessed the first issue. What's the second issue?
Is it the magnetic field?
In a way that does, I would say the magnetic field is partially, what I really should do and what I've done in the past is make a flow chart. Sometimes it's fun to make a flow chart so you can see all the wacky connections. I want to keep it a little simpler today. The magnetic field stems from the internal heat. So you're not wrong, Jenna, you're right. But I was thinking of something that's parallel to internal heat, maybe something that would be helpful for holding on to atmospheres, We kind of talked about this last class, right?
Could it potentially be a stronger gravity? Stronger gravity?
More planet is more gravity. And gravity is good because gravity helps you hold on to atmospheric gas. There are many things that come off of both of these two things. Atmospheres, magnetic fields, you name it. We could keep playing this game. And at times, I have made fun, wacky flowcharts with my students just to try to see the weird connections. Today, I want to keep the message boiled down and simple because I got a bunch of different little modules to do with you. So size turns out to be a fundamental planetary property. Here's another one. Distance from the sun. And this probably needs no introduction. You probably already intuitively know what role your distance from the sun has in the evolution of a planet. Right? Why would the distance from the sun matter?
So that water can remain in a liquid state.
I'm sorry, Ian?
So that water can remain in a liquid state.
Yeah, we talked about that Goldilocks zone idea, right? But it turns out that, let's say we're not just focused on life, which of course we are, but let's say we're just focused on how does Jupiter end up being different than Earth? What if we were just interested in how does a planet evolve over time? Related to that concept, distance from the sun controls your surface temperature, and your surface temperature does affect the evolution of the planet. So this is your surface temperature. That will affect not only whether you have water in a liquid or a gas or a solid, but it also affects other things like what type of atmospheric particles can condense into clouds. You're going to see that the different colorations of the Jovian planets, the stripes of Jupiter, the ammonia haze of Saturn, all really have to do with just your distance from the sun and surface temperature. Do you guys remember what all right, you can't remember what the third one is if I've never summed these up for you before, but I did talk about a surprising property of a planet. Here's a hint related to magnetic fields that does affect the evolution of a planet. And Venus versus Earth perfectly sum it up.
Rotation.
So, Ryan, Jen has got it. Ryan, solar wind would be related to distance from the sun, if anything. I've never really thought to put that in here, but the solar wind flux will be greater towards the sun, but magnetic fields play a bigger role in that. Jenna, you hit the nail on the head. And this is the one you'd never guess, rotation rate. Had Earth not spun on its axis every 24 hours, I'm not sure this planet would be the same one it is today. Certainly, Venus's lack of rotation has had a profoundly bad effect on its evolution over time. Rotation rate will, of course, affect things like your magnetic field, but as I will show in today's lecture, it also relates to atmospheric circulation. And atmospheric circulation, as we hinted at in our Venus homework problem last week, wow, there we go. That's last night's whiskey talking. Circulation, okay? Atmospheric circulation is an important part of creating wind erosion and temperature variations, temperature stratification, okay? What the hell? Let's throw in wind. We'll put it up as wind erosion, which is one of our 4 geological processes. You can't have wind without planetary rotation. Notice that chemical composition is not one of the fundamental planetary properties. It didn't turn out that Jupiter was made of cotton candy and Saturn was made of jelly beans. They're all made of the same stuff, but these are the things that affect the physical evolution of the planet. And why we think about this is we have discovered more than 5,000 planets outside of our solar system today, yet we have no pictures of these planets. We can't see them. They're too far away, they're too small, and they shine only by a very dim reflected light. But we have trickery, ways in which we can measure some of these properties. And if you can do that, you can speculate on which of those planets might be geologically interesting and worthy of a future science mission or something like that. Okay, this is a key takeaway from the course. I know probably lots of you are not planning on taking the final exam, but if you are, these kinds of questions would come into play. Just as a little show of hands today, how many of you are planning on just doubling your midterm grade? I kind of ask this every class, but I just want to get a sense. So most of you are, yeah, okay. And you guys feel good about that. You know you can take the final if you want to take the final. You have no regrets, okay. I don't want to be coercing anyone here. I just want to see what you want to do. Okay, cool. Let's talk a little bit more about atmospheres and planets together. I'm going to erase this with everyone's permission. Okay. I'd like to talk a little bit about the greenhouse effect. The greenhouse effect is related to how atmospheres are heated in the lowest layer of Earth's atmosphere. Let's just pretend I was giving you a test. What are the 4 layers of Earth's atmosphere? Does anyone remember stuff? Or can you slyly look at your notes without me catching you? Layers of Earth's atmosphere.
So I just found it in my notes.
Okay, sure. Read them out.
It is the troposphere,
Yep.
stratosphere, thermosphere, and exosphere.
Okay. Our last class, we sort of tackled the exosphere. In the last class, we thought about particles boiling away into space as they were heated by solar wind ions and X-rays and UV light. And the point of that was that atmospheres leak and they need to be replenished by volcanism. Today, I want to talk a little bit about the lowest layer of our atmosphere, the troposphere. I want you guys to remember that the troposphere is heated by an interesting mechanism. Visible light, especially on a nice warm sunny day like today, comes down from the sky. It heats up the ground rock underneath your feet. The ground rock becomes warm and it re-radiates as a black body. At about average surface temperature of Earth is somewhere around 15 degrees. That's 287 Kelvin or something like that. At this temperature, a black body tends to radiate in the infrared, pretty close to 10 microns, okay? And the atmosphere is somewhat transparent to infrared light. Infrared light can make it to the ground and to outer space, but there are key gases that are really, really good at absorbing infrared light, and those are called greenhouse gases. And I want to give you a sense. I have like a really kind of lame animated GIF here, but it might give you a sort of idea. Molecules of, so what is most of the air we breathe comprised of?
Nitrogen,
Nitrogen, and the second biggest constituent?
oxygen.
Oxygen. Nitrogen and oxygen are molecules that are diatomic, right? And molecules are kind of interesting. Let's just imagine drawing a nitrogen, N2, diatomic nitrogen. You have an atom of nitrogen, and it's kind of connected to another atom of nitrogen by a symbolic imaginary spring. Like springs, if you push the two atoms too close together, they repel a bit. If you drag them too far away, they tend to snap back into place. Of course, there is no spring there. What's really happening is the nitrogen atoms have electrons, which are orbiting around both atoms and are shared. But at the end of the day, the physical force of repulsion and attraction, that equilibrium, is actually quite close to what happens with a spring. A spring has an equilibrium stretch. If you stretch it, there's a restoring force. If you compress it, there's an expansion force. And because of this, nitrogen molecules, like most molecules, not only have energy states where electrons can jump up and down within their own atoms, but they have vibrational modes and rotational modes that can be excited by photons. For instance, it's possible for nitrogen molecules to kind of, I do have a little chemistry set somewhere, but I didn't think to bust it out. A little ball and stick chemistry set, but nitrogen molecules can kind of vibrate in place. And those vibrations are quantized. They're quantum vibrations, just like the energy states of electrons. So you can get a nitrogen molecule to kind of vibrate at one frequency. If you hit it with a photon of the correct wavelength, you can increase its vibration. And sometimes the vibrations will spontaneously decay, re-emitting a photon. I hope that made some kind of sense. There are certain molecules that are wicked good at absorbing infrared photons right around the same wavelength that the Earth re-radiates. And these are called greenhouse gases. Let's look at some of them. I made a quick mention of this before, but it deserves more treatment. Greenhouse gases are molecules whose so-called vibrational modes, I like using some adult talk with you guys sometimes. It's nice to kind of give you the willies with some adult vocabulary like this. Molecules whose vibrational modes are in resonance, that means same frequency more or less, with infrared wavelengths of light. And boy, the pretension is running high today, because that's just another way of saying these molecules are good at absorbing infrared photons. So I have an animation here of what is probably a carbon dioxide molecule. Carbon dioxide is one of the main greenhouse gases that affect temperatures on our planet and on Venus. Boing. See that? We just stimulated one of its vibrational modes. They have these, you'll see that greenhouse gases tend to have 3 atoms in them. So for instance, a water molecule is funny. I have to draw this out, but in a water molecule, oxygen attached to 2 springs of hydrogens. Not only are there vibrational modes that make the hydrogens bing boing around, so the hydrogens can they can boing back and forth in resonance, they can be out of phase with each other, but they also have bendy modes where the hydrogens kind of bounce up and down. In fact, water turns out to be a killer greenhouse gas. It's a very effective greenhouse gas. If you think about it, there's actually more water in our atmosphere than there is carbon dioxide. I don't suppose anyone remembers the relative percentages of water versus CO2 in our atmosphere. I know, but
What?
there's a meaning to this. There's a reason to know these things.
It's 0.4% water and 0.04% CO2.
Yeah, I was reading something the other day. Someone had some. I don't go too crazy with the science blogs and stuff, but I follow a couple of NASA Facebook or Instagram pages, and sometimes people will just post cool information graphics. They'll be like, "Oh, I didn't think about that," and they actually posted a really interesting one on comparing the atmosphere of Mars and Earth, and I learned something. One of the things I was surprised to learn is that whereas let's look at my slide that I showed you guys. So here, these are the correct percentages, but H2O at 0.4% is highly variable in our atmosphere. And you guys know that because when you look at pictures from Earth, from outer space, you can see the cloud percentages are changing back and forth depending on the time of year and what's going on. So this 0.4% is not a hard and set number. It varies around. Here's something else that I did not know until yesterday when I saw this stupid Facebook post or something. The constituent that's most abundant in Mars's atmosphere after the 2% argon is actually diatomic oxygen, 0.4%. Now that is some interesting stuff to think about. Where did Earth get its oxygen?
Water?
No. Believe it or not, Austin, we are in the Goldilocks zone, and our water is protected by being the right distance from the sun and Earth's geomagnetic field. Volcanoes produce water, and the water does not get busted up on Earth. This ain't Venus. This ain't Mars. I thought we had a cool gender reveal party where we talked about the origin of Earth's oxygen. Did we not?
It's something about like the protons smashing and releasing the hydrogen.
That's on Mars.
Oh, okay.
Okay, that's all right. It's probably the fact that I was trying to get you guys ready for the homework and I didn't cover it with enough detail or loving grace. Let's take a look at a key slide from the book that explains the origin of Earth's oxygen. It's life. It's photosynthetic algae. It's cyanobacteria. Can I get a shout out for some blue-green algae? Cyanobacteria. Cyanobacteria are, microscopic organisms that, like plants, absorb carbon dioxide and expirate. Help me out, biology students. Expirate oxygen? Is that the word? I don't know. They poop out oxygen. Okay, that's what they do. And and these things, which exist in great quantities in oceans, ponds, and streams, are actually responsible for the majority of Earth's oxygen budget. It's a sad thought, but you could probably cut down every tree on Earth. You could burn the Amazon rainforest, and Earth's oxygen budget would hardly be affected by a few percent. Most of the oxygen comes from cyanobacteria, and these organisms existed before life was capable of surviving on land. So the cartoon picture goes a little something like this. First, photosynthetic life develops in the oceans, and through a Darwinian arms race, they migrate their way up to the surface of the oceans, where they began to use solar energy and photosynthesis, and they begin releasing oxygen over time. Diatomic oxygen migrates its way up into the atmosphere, where it is struck by ultraviolet photons. Remember that ultraviolet photons have enough energy to photodissociate molecules, meaning they can separate the two oxygen atoms. Then the oxygens occasionally awkwardly reform as O3 or ozone, and ozone turns out to be wicked good at absorbing ultraviolet photons. Ozone becomes an effective shield for ultraviolet radiation, and then temperatures can cool sufficiently on the planet, and you've protected the planet from enough UV light that life can begin to, amphibian-like crawl its way up onto the surface of the planet. Plant life can develop. Animal life can develop on the surface of the continents. You guys, of course, know that this is responsible for which layer of Earth's atmosphere? Test question. Interactions between ozone and ultraviolet light create ozone, and this is responsible for the blank layer of Earth's atmosphere.
The stratosphere?
Booyah, nicely done. The stratosphere. This ozone interacting with ultraviolet light, and this would easily be a test question if you guys were foolhardy enough to attempt my exam. This would definitely show up as a test question somewhere, that the stratospheric bump is being caused by interactions between oxygen and ultraviolet photons. Now, because of this, some planetary scientists believe that finding a stratospheric bump in the temperature profile of a planet is one method of probing whether that planet has some kind of life. People actually see the stratospheric bump, that little increase in temperature, as a signature of life on Earth. Mars does not have a stratosphere. Venus does. In fact, I think there is a picture in the book that shows the temperature scale height diagrams for the other planets. And I haven't shown this slide in like 8 years, but maybe it's time we took a look at it. Look at the difference in temperature and altitude on Venus, Mars, and Earth. Venus, this is basically all troposphere here, and then the temperature starts going up. Mars has a thin atmosphere, so things are a little bit goofy here. It starts off cold, it gets a teensy bit colder, it stays cold, and then it gets a teensy bit warmer as you get to outer space. But Earth has this dynamic switchback. Hey, here's a sneak preview for next week's lecture. Bizarrely, it turns out that Jupiter also has a stratospheric bump, although it's obviously not caused by life, but some planets are weird. But this is considered to be a key indication of life on Earth, that stratospheric bump. Anyways, I digress.
Professor, I have a question.
Please, let's goof.
Why is there so much argon? That's so random.
I actually attempted to address, believe it or not, I badly attempted to address this question 2 lectures ago. And I'm guessing that no one who was here that day remembers it. Let's give it a shot. Let's see if anyone remembers what I talked about there. I didn't do a very good job because I suspect I know why, but I'm not 1,000% sure. Remember that argon sits here. Let's see if students can remember things. Argon sits here, and argon is what type of element?
It's a noble gas. Were we saying that the reason it kind of exists the way it does is because noble gases don't like to attach to other molecules, so it kind of stays pure?
That's the first step. It's chemically inert, so it won't react with things. So any argon on Earth, Ian, must have been present in small doses in the original protosolar nebula. But now Earth forms and crushes itself down into a big rock and makes some atmosphere. Where would the argon be found?
I mean, maybe this is too general, but do you just mean like the atmosphere? Or?
Well, the atmosphere of Earth didn't exist at first.
Oh.
So I was thinking another simple answer, Ian, that it would just be mixed in with all the rock in the interior of Earth.
Okay.
How would it make its way out to the surface?
Volcanism?
Volcanism. So volcanoes pump out a teeny bit of argon. In fact, let me tell you about another infamous noble gas, helium. You know what's funny about helium? Helium, an inert noble gas, is the second most abundant element in the universe. It makes up 28% of the sun. It makes up 28% of all of those badass nebulas you see in the cover of Astronomy magazine, right? See this shit? 1/4 of it is helium, or 1 out of every 10 atoms, I should say. And yet, helium is a rare resource on Earth. And I have a funny anecdote about this. One day, I decided to throw a big crazy party in a warehouse, and we all thought it would be a great idea to get all of these balloons and fill them with helium so they would hover all up and down, and it would be like a forest of balloons, and we were going bonkers. So naive 20-year-old me, or whatever I was, drives out to the party rental store, and I get this big old tank of helium, this giant metal tank, and we're laughing and goofing around, and we throw it in the back of the van, and we take it to the party, and sure enough, we're filling up the helium balloons, and I kid you not, clowns showed up to this party. Clowns were not invited to the party, but real life clowns showed up, and they were huffing on the helium and talking in funny voices, and then everyone started huffing the helium. And the next day I woke up with this absolutely terrific hangover, and the place was a mess, and I thought, oh my God, I got to get the helium tank back to the store. Of course, dummy, younger me didn't realize or think about the fact that as the helium is escaping into the room and into the mouths of clowns, it's being replaced by air, which is much heavier and much denser. So now I've got this like 300-pound metal tank, and we're schlepping it along the street, and we get into the van, we drive back to the party store, and they, the technician there weighs the weight of the tank. He measures how much weight has been added to it because the air is much heavier than helium. And then I got charged like $300, and I hated my life. And I rued the day those clowns came to my party. Now, young dummy me had not considered the fact that helium is a precious resource on Earth. Helium is used for all kinds of cool scientific innovations, like you like getting an MRI at the doctor's office so you can find out where your bone is broken without having to cut your arm open. Well, they have to, cool those magnetic fields with liquid helium. The place that we get helium from today, and Austin, this is kind of a long-winded, funny way of telling you the answer to a very interesting question that you asked. I started looking up after that painful experience, well, where the hell does helium come from anyways? It's the second most abundant element in the universe, says young astronomy student me. Why am I paying so much for this with my head pounding, right? And it turns out because helium's a light and inert gas, if it's in the atmosphere of Earth, it just boils away into space. Remember that problem we did with thermal escape last class? If we calculated the thermal speed of helium in the exosphere, I'm willing to bet it's super close to 1/5 of the escape velocity. And over a geological timescale, any helium that would have been there just boiled away into space. Today, where we get helium from is from natural gas deposits. So you go to some big shale oil field in Texas where there's natural gas coming out, and as they're siphoning out the natural gas for energy, small percentages are just helium that are left over from the formation of Earth from the Protozoan Nebula. And they siphon that off specially, and they sell that for not only technical uses, but also to fill up helium balloons at birthday parties, Apparently, there is a global shortage of helium, and most scientists estimate that Earth is going to completely run out of helium in the next, 50 years or something like that. And that people are actually kind of concerned about this. It's like an issue. So my way of thinking, Austin, is if helium is coming from these natural gas deposits, it must be that there's certain quantities of all of these noble gases just mixed in with the interior structure of Earth. The helium boils away pretty fast. I actually don't know what the deal is with neon. I don't know why there would be neon, but argon is probably heavy enough that when it gets juiced out in volcanic outgassing, its thermal speed is probably so low that it just gets trapped by the gravity of Earth. So that's my long-winded discussion about noble gases, all right? I like that question. All right, let's talk about greenhouse gases. let's talk about molecules that absorb infrared photons. I do remember how the other day we figured out how to run these physics simulations. I believe Ian and Kim helped me work through that. I might need your help again because I'd like to do another one of those if I could. This is a pretty crappy animation, the one that I showed you here, of an infrared photon being absorbed by some kind of carbon dioxide molecule. Let's just look at that one more time. Not only is carbon dioxide one of our principal greenhouse gases, but water is as well. Let's go ahead and label a couple of them, okay? So key greenhouse gases include CO2, carbon dioxide, H2O, water, methane. Everyone loves this joke. Do you guys know what the principal contribution to methane is in our atmosphere?
Livestock.
Yeah, agricultural byproducts, which means cow poop, right? That's right. Livestock contribute the majority of our tiny percentage of methane budget. I actually do not know what percentage of the Earth's atmosphere is comprised of methane. It's probably less than 0.04%. That would be kind of a cool quick Google here. Percentage of methane in the atmosphere. I don't know if they measure it in the part. Oh, wow. Look at that. 1.7 parts per million, or 0.00017. So in terms of our greenhouse effect budget, methane is not as important as these two gases. In fact, why don't we label their percentages to remind us? I should have stacked the other way. Water is 0.4%, but as I noted earlier, it varies. CO2 is 0.04%. And let's just round up to 2. Let's see, this is 3 zeros and then a 2%, right? I was telling you guys that water is 0.4% of our atmosphere, but that GIF that I saw on Facebook said that it's highly variable. And that occurred to me that that's probably true, just based on one day you've got clouds in the sky, the next day you don't. What I was fascinated by, and I would like to just remind us about this before we go away, I was so shocked to learn that Mars had a tiny bit of diatomic oxygen in its atmosphere. Now, that did not come from cyanobacteria. Well, perhaps Mars does seem to have had a giant ocean at its surface, so we can't say for sure. But the other place where it could have come from was Jenna's hypothesis. That's where solar wind ions smash apart water, and some of those oxygens will combine to make O2. In fact, that's the story we told in our previous class. And you know that the reason why Mars's surface is red is because the diatomic oxygen has rusted with the surface. The fact that there's a tiny percentage of O2 still there probably just means that the process is ongoing and it hasn't finished evolving yet. Okay, I want to see if I can do one of these animated GIFs just because they make the day go by. I also want to show a fun video to you guys today too. I hope I can get to all this stuff. I'm moving kind of slow. Let's see if I can just run. I don't even know how I pulled this thing off. I've been terrified of closing it because those gases are still boiling away there. Let's see if we can get one of the other ones to work. So I have one on water molecules. An example of how water molecules absorb infrared light is related to, wait for it, your microwave. Can I just run this? Is that how I did it last time, guys? I can just run it now? Hell yeah. Okay. This is cool. Listen, I've got this friend, right? And she's terrified that the microwave is nuclear irradiating her food. So she won't cook anything in the microwave. And it's annoying because sometimes I just want to make a cup of tea or something, right? And she doesn't want those poisonous nuclear waves affecting her food. One day when she was forced to use the microwave, she said, Brendan, I opened up the microwave too fast and I put my hand in. Did I nuclear irradiate my hand? I said, well, did it get hot? She said, no. And I said, I think you're fine. See, microwaves aren't using nuclear waves, whatever the hell that is. They're using photons. They're using low energy, long wavelength infrared photons that just happen to resonate with the vibrational modes of water. Now, I've got to give a handout to whatever grad student made this little animation here. It's cute, but it pisses me off because I would have liked to see the vibrational modes of the water molecules as well. So if you're ever out there and you're going to listen to this, do even better, okay? Let's activate our microwave. Looks like it's got a frequency of about 1 millihertz here or something. Let's turn the microwave on, and there's a single water molecule, and boop, we're getting it. This is the rotational modes, but they also have vibrational modes. We could do a line of molecules. Let's turn on our microwave. Boop, here we go. And we start jiggling them water molecules. Now, if you know how to use a microwave, it can be a very effective cooking tool, provided you don't dry out your foods. And you can use water in a clever way. The molecules, of course, gain kinetic energy, and then they crash around into the pieces of beef stew, and the whole damn thing becomes hot. Here's an interesting fun fact. You can take a perfectly dry plastic fork, put it in your microwave for 2 minutes, go in and touch it, it'll be cold. There's no water molecules in the plastic fork. There's nothing for it to absorb. This means that you guys have experience already, right? You already have experience with the greenhouse effect, because the greenhouse effect happens when water molecules and carbon dioxide molecules start absorbing those infrared photons from the ground. And we're going to do a little note on this here because I think it's important to understand how this works. That's why I'm taking my loving time with it. Let's look at the picture that I love from our slideshow here. The greenhouse effect is best described in this simple animation here. Visible light comes down and it heats the ground. The ground gets warm and re-radiates as a thermal black body at infrared wavelengths. Infrared photons travel up into the atmosphere. They're not very effectively absorbed by nitrogen or oxygen, but they are absorbed by those trace gases, water molecules and CO2. The water molecules and CO2 then go mosh pinning around. They heat up the other molecules. Eventually, through collisions, they slow their vibrations. They re-radiate infrared light at slightly longer wavelengths, and eventually the infrared light escapes into space. Let's do that as a quick note. That's something we would like to remember from this class. And then I'll tell you some fun facts. Okay. Visible light heats ground rock. Then the ground re-radiates as a black body. You guys are getting to the point where I can use some of my fancy vocab terms and you don't get too scared. At infrared wavelengths, somewhere near the 10 micrometer range. Then infrared light is absorbed by, in our case, trace greenhouse gases, such as CO2 and H2O. The greenhouse molecules, greenhouse gas molecules collide with, let's just keep the notes simple. I want to say air, right? N2 and O2, heating them up. And then, as these molecules lose energy, how do I want to say this? The bashed up greenhouse molecules, the Sorry, words are failing me today. Greenhouse gas molecules, and let's just call them de-excited. That's how you would say it. De-excited radiate infrared light into space. So there's just enough Jenga blocks in this logical chain where I thought it was worth us taking a note on it, because since you guys are learning it for the first time, that's a lot of steps in the logic to keep in track. So it's kind of nice to have this as a note. Now, is the greenhouse effect good or bad for life on Earth? What do we think, Ian? Greenhouse effect, good or bad?
I think there's a fine line for when it's good and bad. I think at normal levels, like it has been for most of Earth's history with life, it's been good. But if it gets too intense, then we're gonna turn into Venus.
Exactly. And let's look at a cool slide. I don't know if this is still in the book today, but it was years ago. Let's look at calculations of what Earth's global temperature would be, what it is today, and then in this column we have what I would call the delta T. A delta T is a temperature differential caused by a greenhouse effect. Remember that I taught you guys a formula in a previous lecture for the no greenhouse surface temperature, and I posed that as how hot is my rock in space based on distance from the sun and albedo. Well, the answer is negative 20 degrees Celsius on Earth. Without those trace greenhouse gases, Earth would be below the freezing point of water. And maybe not all of the oceans would freeze, but you could definitely put yourself into a snowball Earth phase if you kept that kind of an average global temperature. Sorry, I'm getting dings. Someone loves me today. All right. Today, sorry, let's call it negative 15 degrees Celsius. I like to keep the numbers easy to remember. So Earth temperature today would be negative 15 degrees Celsius, but because of the greenhouse effect, it's 15 degrees Celsius, which means a delta T. Do you guys see how the book made a mistake here? I love it when I can correct this. When you do temperature differentials, it's customary to put the degree sign after the Celsius. So the way that they should have written this is, and this is a thing, physical scientists make an issue out of this, 32 Celsius degrees. This tells the scientists that you're not talking about 32 degrees Celsius. You're talking about a change in temperature of 32 Celsius degree increments. I hope that made sense to you guys. In other words, our 0.4 water and 0.04 CO2 is responsible for 30 Celsius. Now, how many degrees would that be in Fahrenheit? How many Fahrenheit degrees would that be? If 9/5 is the ratio, then call it a factor of 2. That's a net change in what? Approximately.
64 degrees Fahrenheit.
Something like that. Yeah. Your Fahrenheit degrees, right, Jenna? It's a temperature differential. That, when you think about it in terms of Fahrenheit, that's a huge effect, right? And these gases exist at small trace percentages. Now, I want to talk to you guys about something. One of the best places in the world to do astronomy turns out to be the mountaintops of Hawaii, in particular Mauna Kea, where you can go and visit the Keck twin binocular telescopes. If you look at a couple of pictures of the Keck binocular telescopes, first of all, these things are just worth talking about because they're freaking cool. It's a twin pair of telescopes. Okay, let's see if we can find a super high res picture here. Oh, wow, 5,000 pixels, baby, give it to me. All right, here, let's see if we can get this 5,000 pixel. Nah, you're gonna be lame like that, aren't you? Each telescope mirror has a diameter of 8 meters. Think about that. Each telescope has an 8-meter diameter, and there's not one of them, but 2, so they can function like a set of stereo eyes and take slightly different measurements of nearby stars. This is one of the best damn telescopes in the whole world. It rivals Hubble. And one of the reasons why you build a telescope like this on the mountaintops of Hawaii is not only for reasons of light pollution, but reasons that you can clearly see in this picture. Why might Keck, at an elevation of 8 kilometers or something, 7 or 8 kilometers up, be a great place to host an observatory?
Could it be low obstruction? Very little
That's-
obstruction from nearby, like, for example, there's not much mountaintops in the area, so
Okay, but you're thinking of something else that obstructs observations.
Above the
Right?
cloud line.
You're above the freaking cloud line. You're so far up that if you have a cloudy day, no big deal, bro, because the clouds are below you. Actually, what's cool about being an astronomy grad student is sometimes the professor that you work for would get some time on the Keck telescope. And then rather than, they've got to go home to their wife and kids or whatever, or their husband and kids, and they've got other stuff going on. They got to write research proposals. So they'll oftentimes send their grad students to Mauna Kea to do the observations. Now, the first time you're a grad student doing this, you're all excited and you're like, going to go to a big telescope. This is going to be an awesome time. But what happens is you fly from, say, Boston out to the Keck telescope. You're on this like 10-hour flight. You're totally jet lagged. And now you get there and you've got to drive up the mountaintop where the oxygen is decreasing and your brain's getting kind of stoopy. And now you've got to prepare yourself for a night of no sleep. And you're up there at 8,000 meters, right? Or whatever it is, or 7,000 meters. And you had to select the targets that you're supposed to observe, but oops, you screwed something out. And now you're sitting there trying to recode your software with the oxygen deprivation and the sleep deprivation, and your brain's a little addled and you're going to get chewed out. And then you got to come down the mountain at the end of the night and get back on the plane and fly back to Boston. So it's a harrowing experience, although it's freaking amazing, a wicked cool way to earn some money. And the point I'm trying to make is you're going to need some coffee. And it turns out that there's another thing that the mountains of Mauna Kea are famous for, and that's delicious, nutritious Kona coffee beans. Now, Kona coffee beans, if you're a coffee enthusiast like me, they're some of the most expensive and delicious beans of coffee on the market because they grow on the side of a volcanic mountain, an active volcano, which is rich and fertile with nutrients from this basaltic soil, right? So here's these coffee bean plantations. I only know about Kona coffee because one of the grad students who did this observation run brought back a little freeze-dried bag of it right from the plantation. And one day I just kind of made some coffee in the break room and I took a sip of this and it was like thunderbolt. Like I was rocked. I was like, I never knew coffee could taste like this. Go into a store and buy some Kona coffee. It's like twice as expensive as normal coffee. Also for reasons that have to do with, labor issues, but whatever. I want to show you guys a slide from one of my graduate texts, or maybe I can't remember where I found this. Maybe it was your book. And, observatories like the Keck Observatory, they every day have usually like a little weather station on them, and they record the temperature and the observing conditions, in case they need to recreate what the conditions were during their observation runs. So they measure temperature, percent humidity. They'll measure concentrations of carbon dioxide and other trace elements in case that could affect the science of your observations. And of course, they've been keeping data there for years on the concentration of CO2. And I want you guys to look at this sort of terrifying little graph here. And this graph is now out of date. There are more sophisticated versions of it, but it's good enough to give you all the idea. These are measurements of concentrations of CO2 on the mountain of Mauna Kea from the year 1960 to the year 2000. Now, do you see these little oscillations where CO2 is going up and down and up and down? Those are changes in carbon dioxide levels due to the growing cycle of the Kona coffee beans along the plantation on the mountain. In other words, this is what the plants and what nature is doing to CO2. When the plants are in bloom and they absorb a little CO2, it goes down. When the plants are out of season, you get a little slight increase. So those changes, that oscillation is due to the Kona coffee beans. And then superimposed after this, and of course, you guys know what's causing that increase, right? You, of course, know what's causing that, right? Don't you?
Warming.
Human beings, carbon
Mm.
emissions from everything from cars to you name it, okay? But a lot of it has to do with cars, honestly. Cars and other kinds of fossil fuel burning. Cars and you know, coal plants, things like that. Now, what scares the willies out of me is, let's make a crappy analogy. If in 1960 the CO2 was 300 parts per million, and we got a delta T of 30 Celsius degrees, that kind of suggests in a lame way that every 100 parts per million gives you about 10 Celsius degrees. We have gone up now well past this today, and temperatures on Earth have also begun to rise. Of course, temperatures from year to year fluctuate on Earth, which people always forget about. But if you graph over a long period of time, this is 1850 to 1950, you'll notice that you can have some wild swings in the average temperature of Earth from year to year, but not only for hundreds of years, but for tens of thousands, hundreds of thousands of years, Earth's global temperature has actually remained quite stable. It's fluctuated about the 15 degrees Celsius mark. Up until about here, where the temperature has slowly been going up. This was from when I first started teaching the class 10 years ago. This was a slide. I haven't updated my slides in a while, from 10 years ago when I started teaching this class. At that point, we'd hit the 1 degree mark. Today, we have hit the 3 degree mark. And many climate scientists believe that once you go too far past 3 degrees Celsius, Earth could potentially go into an irreversible set of climate change. Remember, of course, that Earth traps a lot of carbon dioxide on the seafloor bed. And I'm pretty sure that we had a lecture where we covered the carbon cycle, the CO2 cycle on Earth, right? Do you guys remember this picture? Did I do it during an office hours, or did we actually do a bloody thing on this? What's the point of this story? If I show you the picture, can you tell me the story?
I could give it a shot. So basically the CO2 in the atmosphere is precipitated down into the oceans, which gets folded under plate tectonics into volcanism, which re-emits it into the atmosphere. So that's sort of the cycle.
Right, but the reason, yes, you did a wonderful job explaining this. The reason why Earth does not have the same CO2 levels that Venus does is because we have a Venus's worth of CO2 trapped there. And only 0.4% of our atmosphere is CO2. Sorry, wow, I screwed that up. Correct me if I'm wrong. Only 0.04% of our atmosphere is CO2, right? What percentage does CO2 make up in Venus's atmosphere? Anyone remember?
Was it 20 something or no?
Oh, no. You're missing the point here.
It's 96%.
96%. Thank you. Notes from the underground there. 96%. Now let's look at that same slide. Ooh, I'm not sharing my thing with you. Hold on. I'm having a sort of a zing zang zoom lecture here today. I'm bouncing all over the place. But there's a madness to my method. Okay. Venus should have a no greenhouse temperature of negative 43 degrees Celsius. Okay, there's clearly something flawed about this calculation. Should the surface of Venus be warmer or colder than Earth's in the absence of a greenhouse effect?
I was actually going to ask you about that, because I was like, is there a reason why it's colder, even though it's closer to the sun, should be warmer?
If you remember the no greenhouse temperature, the no greenhouse temperature has a reference 280 Kelvin multiplied by the fourth root of 1 minus the albedo, right, over distance. Notice that they're pretending that this is the no greenhouse temperature, but they're using a global average albedo of 72% because they're using the reflectivity of the cloud tops. You guys remember what Venus looks like, right? Do I have a picture of it here? Venus looks like that. So they're using the CO2 clouds, but the CO2 cloud, that's 96% CO2 and it's no greenhouse temperature. Nah. What should the average albedo of Venus be like? This requires you to know something about albedos. It's kind of like a test question or something. Let me show you the picture from our planetary geology. Like, come to me, planetary geology.
I mean, so if I remember seeing pictures of this surface, it's pretty dark, so it'd probably be on the lower end.
Exactly. So I'm very impressed. You knew exactly what I meant. It's black volcanic rock, just like the surface of the moon. Remember that the moon's average albedo is like 5 to 7%. So actually Venus, what they should have done to make that calculation cooler, they should have used the albedo of the rock to imagine what it would have been like beforehand. Anyways, Venus today, if you look at my slide again, the average sorry, nope, too many slideshows, too much to juggle. Planetary atmospheres. Today, Venus's global average temperature, did they do that in Celsius or in Kelvin here? F547. Venus's surface temperature is 513 degrees Celsius. I'm sorry, well, sorry, 400, I just screwed up. That didn't sound right to me. 470 degrees Celsius, which is responsible for a delta T of, here's how I would do it right, so you don't make the mistake that I just did, 500 Celsius degrees of temperature differential. Could you imagine? By the way, that's hot enough to melt lead. A block of lead would liquefy on the surface of Venus. Not to mention the atmospheric pressure would kill you, right? I would like to not have Earth turn into Venus part 2. That wouldn't be nice, okay? Another thing to think about that the book points out about climate change is, let's say you just raise let's say you melt a little piece off of Antarctica. I don't know if you guys have ever seen the Larsen ice shelf in Antarctica just breaking off and drifting into the sea. The New York Times had a video of the Larsen ice shelf collapse. And this was like last year or something. I just woke up one day, I'm looking at the New York Times. They have a video of basically this huge ice shelf in Antarctica just totally cracking and disintegrating to the sea. This isn't, the actual pictures are beautiful because it's just it's beautiful to look at aerial photographs of the Larsen ice shelf. But this chunk here, it was 6,000 square kilometers of the Larsen Sea ice shelf in 2017. So it was a few years back, just formed this huge crack and whoop, just dropped right into the sea. If you think about life on Earth lives along the coastal waterways because fish are easy to catch and an abundant energy source, and then there's maritime trade. You live in Providence, or I live in Providence, Rhode Island, and other people live on other coastal cities like Los Angeles. And yeah, that's crazy, right? That's totally crazy. So it's not good for humans if the sea levels rise. And that can also, another thing that's kind of spooky to me is if you put more water vapor into our atmosphere, we now know that water vapor is a greenhouse gas. And that's why you see as temperatures rise, all of these storms, all of this El Nino activity and these hurricanes, it makes more mischief. So these are things that we have to think about to be responsible citizens. Sometimes people are mistaken and they think that climate change is a political issue, but climate change, climate science, it's a scientific issue. It's one that you take measurements and you evaluate the data. And the overwhelming consensus of climate scientists today, 99.9% of them, is that changes in carbon dioxide level are human caused. And they're things that we must manage appropriately if you don't want to live in Kevin Costner's water world, okay? Go watch that movie. Get some web toes and see that movie so you can see what your future is going to look like, okay? You're going to be floating around in some driftwood cities. Anyways, cool, interesting. Oh, I have another science. I don't know how I'm doing on time here. I'm getting close to the edge. Can I ask you guys another question about the greenhouse effect? What's up with Mars here? This should be obvious, but I just want to make sure your brains are still working. Mars is no greenhouse surface temperature. But all right, first of all, what percentage of Mars's atmosphere is CO2.
Isn't it like 95%?
Yeah.
Exactly. Basically the same as Venus. But yet, unlike Venus, Ryan, its average surface temperature should be negative 55 degrees Celsius. The real surface temperature is negative 50 degrees Celsius, which is a temperature differential of 5 Celsius degrees. Why does Venus have a 500 Celsius degree temperature differential, whereas Mars only has a 5 Celsius degree temperature differential?
Is it because Mars has such a thin atmosphere?
Yeah, that's got to be it, right? There's just so much less atmospheric gas on Mars that its greenhouse effect doesn't really change things that much. I do want to tell you something kind of interesting. This is going to come up in today's homework. So I'm helping us do the homework right now, and you don't even know it. Mars has an interesting set of circumstances for its climate, which is unlike Earth's orbit, which is almost completely circular. It has only a 2% eccentricity. Mars's orbit has a 9% eccentricity. So Mars actually does have a significant drift towards and away from the sun. I want to show you a picture. I'm not exactly sure which slideshow it's in, but it relates to one of your homework questions today, and I think it's just kind of interesting. Here it is. Let's talk about seasons on Mars. Now, when you guys were just little shavers back at the beginning of the semester, I couldn't tell you all the truths all at once because they were too complicated. So I told you a little lie, and I told you a little fib, which was seasons are caused by axis tilt, full stop. But I meant on Earth, and I meant on planets whose orbits are circularized. Let's see what's going on with Mars. Like Earth, not only does Mars have the same rotation rate of 24 hours, its axis tilt is super similar to ours at 25 degrees. But Mars has a high eccentricity, and I want you to watch what happens here. When Mars is furthest from the sun, the northern hemisphere is pointed towards the sun, okay? The southern hemisphere, so notice that the northern hemisphere of Mars right now is summertime. Can you guys just explain that to me? Why is it summer in the northern hemisphere of Mars in that configuration?
It's receiving the most direct sunlight because of the way it's tilted.
That's right. That was from our chapter 1 lesson. Meanwhile, the southern hemisphere is in wintertime because it's pointed away from the sun, but it's also farther from the sun. So you get a really brutal cold winter in the southern hemisphere. Here, the summers are slightly cooler. Similar to this, when Mars is at its closest distance at perihelion, now the southern hemisphere is pointed towards the sun, meaning summer is unusually warm. Meanwhile, the winter on the northern hemisphere is mild. Now, you could see from the surface of Mars that it once had liquid water on its surface, and it probably had a more substantial atmosphere, and it probably had a more substantial greenhouse effect. Mars was probably not as cold in the past. If you were liquid water and you did not want to freeze out or boil away, where would you go? Where would you stay on Mars to keep yourself liquid?
Probably the northern hemisphere.
Exactly. And to add to this, what did we see? I always like to end the class with a kind of, a revelation, if you will. And my version of that today is here. If I was liquid water and I wanted to stay liquid and not freeze out or evaporate, I would go, says Ian, to the northern hemisphere. And let's look up here. What do we see in the northern hemisphere of Mars?
That's where all of the old oceans were.
That's where you see all of this erosion and rivers spilling into this giant planitia. And look, it almost looks like Mars was like an ocean world where the ocean was all in the northern hemisphere. The southern hemisphere was this landlocked Pangea-like continent that couldn't fracture because of plate tectonics. And Mars probably, could you imagine being able to have your GoPro sent back 2 billion years ago on Mars? It would probably be this atmosphere, water-like world. Who knows what kind of mysteries could have been there? This is why people are obsessed with Mars, why we send so many rovers to Mars. In fact, You guys see where they put the very first landers. Look at this. I may have made this point before, so I apologize if I'm saying the same thing again. But you could go anywhere on Mars. First, you send Pathfinder there. Then you send another mission to Mars and you send it there. Why not land on the top of Olympus Mons? Why not visit the South Pole or the North Pole? Why do they keep plunking down in the same place?
Probably because we're not able to see any other planets really with liquid water, and this is the best evidence of it.
Yeah, kind of. In other words, if you were interested in finding life on Earth, where are you most likely to find life? Not at the top of Mauna Kea, but along the coasts, right?
Yeah.
You have lots of life. The coastal waterways are teeming with life. And so if they're going to find these, or by the way, the Curiosity rover, let me just show you guys what's going on here. Planetary science time. Where's my... They sent the Curiosity rover to Gale Crater here. That's where Curiosity is. Notice that's probably another place where they would have expected water to have pooled in the past. You can almost see some kind of like erosional channels heading in there. The rover that just landed, the Perseverance, is in Jezero Crater. And Jezero Crater is somewhere, it's somewhere over here. That's where Jezero Crater is. So notice that they keep sending these missions to different places on Mars where there probably was coastal waterways, thinking if we're going to find the microorganisms buried in the permafrost, if life could have evolved on Mars independently on Earth, that means them aliens are out there. 2 planets in our solar system where life spontaneously originated. That means the galaxy is teeming with living organisms. And that's an exciting and creepy thought, you know? Okay, so let's leave it there for now. We're going to do a hybrid homework. Ian, do me a favor in case I get caught up in my tea break. Could you guys just take a second and write these numbers down in case I've got to do this on the fly? You know how I am. I do everything on the fly. Could you guys write down these questions before we tea break here? Oops. It's Chapter 9, 50, and 61. Chapter 10, 51, 63, and 64. These are not as hard as our previous homeworks, and I think these are just questions that'll re-emphasize the stuff we learned about today. On Monday's class, we will do the Jovian planets. Jovians or bust. Okay, you got those? Let's take a little break here. I'm going to pause for, it's 1:34, 1:45, 1:50. We start our homework, and we'll try to go quick. All right, guys, I'll see you in a little bit. Okay, Astronomy 1010, we're back. It's time for homework number 11. It's a combo homework from chapters 9 and 10. The students and I have just entered in this new set of questions that we'll be doing today. Let's get them up on the board. Just got kind of cloudy out, so let me add a bit of light. All right. As usual, we're going to put our name. We're going to put AS1010 so I know what the hell you are and who you are. Put your section, whatever that is. And I believe this is homework number 11. We'll be doing 2 problems from chapter 9, 50, 61. A couple problems from chapter 10, 51, 63, 64. And these would be similar to the kind of things you'd be asked on a test. So it's okay that you're not taking the test because you're learning and you're practicing here and we're doing it right. Ian, since you're the first box for me for just a second ago, you were anyways, why don't you read us chapter 9, number 50?
Cool. Chapter 9, number 50 is predictive geology.
Okay.
Suppose another star system has a rocky terrestrial planet twice as large as Earth, but at the same distance from its star, which is just like our sun, and with a similar rotation rate. In 1 or 2 paragraphs, describe the type of geology you would expect it to have.
2 times the mass of Earth, a distance of 1 AU, and a 24-hour rotation. and we want to answer questions about geology. All right. Jenna.
So just from our notes, I'm thinking that it'll have a greater internal heat and stronger gravity.
Yep.
So now I guess like how does that affect geology?
Right.
Yeah, that's the starting point I got.
Well, we did even keep that in our notes too. So you're saying exactly the right things. This is how we want to be thinking. Nori, I don't know if you know this, but you're sideways today. It doesn't really bother me so much, but I don't know if it bothers you. Okay. What
My
if you-
phone's charging, so I this is what I'm working with today.
Okay. All right. We can work with you. If you're twice the mass of Earth, would your geology be the same as Earth's, or would it be different?
It would be different for
It
sure.
would be different. That's one of the big points of this question. But okay, what are our 4 geological processes?
Volcanism, plate tectonics, impact craters, and erosion.
Okay. So
Um,
let's do it by the numbers. Impact cratering. What would the effect of having twice the mass of Earth be?
Not much of a difference, probably,
Oh yeah, not much.
because that's not really necessarily impacted by size.
It's not impacted by size. Well, one way in which you're correct is that today, remember, Earth does not have a ton of impact craters, right?
Yeah.
So impact cratering is already quite low on planet Earth. If you look at a global scale, Venus and Earth are relatively blemish-free. Mars, of course, has highlands from the heavy bombardment period. And yet there are interesting craters on Earth, by the way. I think that lecture got kind of chopped at the edge of class. But I told you guys, I think, that I went to undergraduate school at the University of Arizona. And did I show you guys Meteor Crater, the one that's out in the deserts of Arizona? I got to visit this when I was a student, and it was just totally wild. The thing's maybe like a mile in diameter. It's like 60 million year old crater. I'm actually maybe less than that. It's on private property, so you go out to this thing in the Badlands of Arizona, and you stand on the observation lounge, and you look over this thing, and it's just completely wild. This is Meteor Crater in Arizona. This is Wolf Creek Crater in Australia. Did I show you guys these craters before? Does anyone remember this? No? What do you, can I get a high-res picture? What would you say is the difference between Wolf Creek Crater in Australia and Meteor Crater in Arizona? They're comparable in size, but
The one in Australia seems like it's been eroded more. It looks a little bit smoother.
yeah, so this would be the older crater. Erosion has been chipping away at this thing, right? Another famous one is the Manic Kugen. How do I do this? The Manic Kugen crater. This is in Canada, and it actually can really only be seen from like the International Space Station. And look at this thing. It's like an ancient impact site that's now become so eroded that it's basically just turned into a circular riverway. If you were actually on the ground, you wouldn't even realize you were standing in an impact crater. When you see people like taking canoe trips up there, you're just like a little ant sitting here, right? And it's not even obvious that you're at an impact crater site. It's not until you get to outer space and look back down that you're like, oh shit, that's an impact site, right? Okay. My point being that Earth doesn't have as many craters as Mars, but it has some craters. So let's go through it. Let's do impact cratering last. What do we expect to happen to volcanism?
Actually, thinking about what you just said, did you mean to say that impact cratering would show up less because there's more other geological activity?
It could only be reduced.
Yeah.
Now, impact cratering is not a dominant surface feature of planetary Earth. So in a way, Ian, you were correct in saying it wouldn't really matter but the reason is not about size. It's about there's going to be more active geology on this planet, right?
Yeah.
So volcanism?
Increase.
There would probably be more because of greater internal heat.
Plate tectonics?
Same thing.
Yeah, plate tectonics does require water. So one of the tricky things about this, as far as I'm concerned, is if this planet has more active volcanism, it's going to have a thicker, denser atmosphere. And what effect does that tend to have on a planet? From today's lecture.
Heat up more, I guess.
Yeah, it probably would have more greenhouse gas, and just think about how Mars hardly is affected by its atmosphere because its atmosphere is thin, but Venus has a huge thick atmosphere and it's really heated up. More atmospheres tend to mean warmer planets. So I would be concerned that if you baked the surface of the planet dry, all the water goes into steam. You might do a Venus kind of thing where the lithosphere could thicken up, but we'll probably assume that it had active plate tectonics. There's probably going to be greater levels of erosion because we have the same rotation rate, but a thicker atmosphere. Remember, I didn't quite get to atmospheric circulation today. That was one of the last things I wanted to do. But we talked in a previous lecture about these Hadley cells. And maybe I'll start off next time with a little tidbit on the Hadley cells. But, oops, that's not what I wanted to have happen. I'm going to start writing in a second. Just let me kind of build up here. Remember that on Earth, the twisting Coriolis force fractures Earth's atmosphere into these small circulation cells called Hadley cells. Because Venus has no rotation, it only has one Hadley cell per hemisphere. And even though this mixes the atmospheric gas around very homogeneously, it doesn't lead for a lot of wind. There's not a lot of wind on Venus, except if you go way high in the top of the atmosphere. Here's the point of this problem. Just because it has volcanoes, earthquakes, and wind erosion does not make it Earth 2.0. This would be a much more dynamic and violent planet. If I can think about it, you know, for old fuddy-duddies like me, you think of like from Star Trek, like the planet Vulcan, which has like all of this active volcanism. Or maybe for the younger kids in one of those newer Star Wars movies where they have that lightsaber battle over that volcanic world full of lava, right? This would be a sort of violent planet. I know you guys know what I'm talking about, all right? So don't pretend like you don't. This would be a planet that would have a violent and very intense geology, but it still could, in theory, support life. If Earth, or let's not say Earth, if a planet had twice Earth's mass with a similar distance and rotation rate, we would expect a much more geologically active surface and a thicker atmosphere. Let's just add a couple of qualifying sentences. Volcanism would increase. Would surely increase with the increase in internal heat. Lithosphere, the lithosphere would be thinner. The lithosphere would be thinner and prone to fractures. I'm just going to slop it all up there without a lot of artistry today. The increase in volcanism, the increase in volcanic activity would result. I'm going to have to continue back up here, guys. Hopefully my handwriting's okay today. Can I erase the first 3 sentences safely? You good, Nori? All right, okay. Kim, I'll assume you're good too. The increase in volcanic activity would result in a thicker atmosphere, which could raise surface temperatures. Planetary rotation, however, would keep the surface cool and erase what little cratering might be present. Excuse me, I'm going to add one more sentence here, so I'm going to take a little more real estate. I'm just going to chip off a couple of these here. In short, we would expect a planet much more geologically active than Earth. I think I already said that, but I'll say it again. With much more active geology than Earth. In fact, here's why I'm, because the universe, because the galaxy is so large and full of so many stars, probably any freaky thing that can be found out there is going to be found out there sooner or later. We refer to such planets that this problem is referring to as super Earths. One reason to be skeptical about super Earths is you'll remember that when we calculated the thermal speed of hydrogen by accident in Earth's atmosphere, we discovered that while hydrogen was above 1/5 of the escape velocity, it was still pretty close. It was like 2,300, it was 2.3 kilometers per second. If you had a planet with twice Earth's mass, that planet would be very close to being able to capture hydrogen. And as a result, it probably would actually be more of a Jovian. However, it is possible for planets to form close to the sun and then boil away a good fraction of their gas. These planets that we discover are called super Earths. So the teachable moment here is super Earths. We've found several of them outside of our solar system, and we try to imagine what their geology would be like. I was hoping they would show you a graph of some of these super Earths. This one is a little bigger than Earth. This is 2.4 Earth radii. This is 2 Earth radii. So notice that they even kind of, they're showing them as like possible gas giants. They're kind of on the boundary between terrestrials and Jovians. However, if they form close to the star, there could be enough heating to boil away that hydrogen and helium and leave behind the super Earth. So it's totally within the realm of possibility. Okay, we knocked that one out. Can I erase everyone? Any objections? All right.
Hold on.
Let's see, Jenna, how do you feel about reading S61?
Okay, 61, more plate tectonics. Consider a seafloor spreading zone creating 1 centimeter of new crust over its entire 2,000 kilometer length every year.
Okay, why don't we pause for a second and let's do a little picture drawing. seafloor spreading happens along places like in the Atlantic Ocean. I may have briefly mentioned the Mid-Atlantic Ridge. And the Mid-Atlantic Ridge is a place where, if you look at this very quick slideshow, it's along the middle of the Atlantic Ocean, and it's a place where the Atlantic or the underlying mantle convection basically leaks up to the surface of the planet. I have a better picture than this, but we'll go with it, okay? We'll just go with this so that I don't delay this any more than necessary. The Mid-Atlantic Ridge is at the bottom of the ocean, and underlying mantle convection pushes asthenospheric basalt, basically like an underwater volcano, but instead of a volcano, it's like a long channel, and it pushes this material up onto the seafloor where it becomes new seafloor crust, and then plate tectonics pushes it apart. We call this seafloor spreading, and that's what this question is about, is calculating some seafloor spreading. That's the term that geologists use. Let's draw a picture of this. We'll have kind of like one tectonic plate. We'll just kind of crudely draw it as a rectangle, okay? And then there's this other tectonic plate, okay? And they've given us some dimensions. So what's happening is we're creating new material. Jenna, can you continue to read so we can get the givens?
Mhm. So 1 centimeter of new crust over every year. How many square kilometers of surface will be created in 100 million years?
What do they give us as the length of this?
1,000 kilometers.
2,000?
Yes.
All right, so we'll imagine that this dimension here, this will be good for Nori, who's doing the class sideways today. 2,000 kilometers, okay?
Yep.
There you go.
And so it's asking how many square kilometers of the surface will be created in 100 million years, and what fraction of Earth's surface does this constitute?
And they want to know the square kilometers or how much surface area. Now, I can think of a way to do this problem. Do you guys know what to do here? How do you calculate area in a floor plan in a house?
Length times width.
Okay, so let's call this dimension the length, okay? And we'll call this direction the width, right? So we have area, length times width. That's length times 2,000 kilometers. What are we going to do about the length part? I was thinking this would be like wicked easy, right? Like so easy, I don't even have to tell you what to do. It's so easy.
Oh, sorry, what was the question? What are we trying to find? Would you just ask?
That's a great question. I don't know. I got confused. I spaced out.
Me too.
Someone's got to keep us on track. Can't go with me.
Well, we're trying to find the length, or yeah, the length.
So that we can find the area.
Yeah.
Okay, so how do we find the length? They didn't give us the length. They were cruel to us. They were mean.
Would you do like the amount of centimeters and times the amount of time, perhaps?
Yeah, just distance equals rate times time. It's the oldest trick in the damn problem-solving book. Sorry, I put kilometers up here, but this was a time in years. That's definitely my whiskey-addled brain trying to.
Oh, happy birthday, Professor, from Jennifer.
Yeah, thank you so much. I got involved in some hijinks shall we say.
I assumed as much.
So let's try that. We have a time in years. We have a velocity in centimeters per year. So I'm going to put this right into the area calculation. We have 1 centimeter per year times 100 million years. Oh, snap. We got a little units problem here, don't we? Time 2,000 kilometers. I think we should deal with some units before we go further here. If we're trying to calculate a percentage of Earth's surface, should we want our area to be in centimeters squared or in kilometers squared?
Kilometers.
Kilometers squared. You yourself
Yeah.
pointed out earlier, Austin, that the Larsen ice shelf is what, twice the area of Rhode Island. So you
Right.
must have been comparing square area, square kilometers.
Yeah.
So what's the conversion from centimeters to kilometers? Do y'all remember that?
Is it 100? Oh no, to kilometers would be 10,000?
It's
100,000?
10 times, it's like times 10 to the 5th.
10 to the 5th. And what is 10 to the 5th power? Not 10,000, but
100,000.
100,000. Good. Okay, so now we're talking turkey. So we're going to do 1 centimeter per year times 1 kilometer over 10 to the power of 5 centimeters. We don't need a calculator for this. Times 100 million years times 2,000 kilometers. Do you guys know how to do this in your head?
Yes.
So 100 million minus 5 zeros, what will that be?
2 zeros. No, much more than that.
No. What do you get if you do 100 million over 10 to the 5?
1,000.
You get 1,000, because this will be 10 to the 1, which is 10, and 10 times 100 is 1,000. So what do you get if you multiply 1,000 by 2,000?
2
million.
Square kilometers. Nice. So our answer is 2 million kilometers squared. That sounds like a lot. We're going to calculate its percentage of Earth. I mean, I bet Texas is 2 million square kilometers, right? Maybe.
I don't think so. Rhode Island is like 1,200, so
Square kilometers?
yeah. Square miles, I think, which would
Oh,
be even.
come on.
Oh, well, that would
Only
be more.
losers work in imperial units. That's what I say. Okay. Hold on. I think they give it to you in square kilometers right on the wiki page. Okay, you're right. Sorry. So Texas is 20,000 square kilometers. That's a 1/100th of the area we were calculating, right? What do you think about the United States?
Gotta be like 10 times that, maybe 15.
Oh, wow. The United States is 9 to 10 million kilometers. Interesting. All right, let's calculate this as a percentage of Earth. Have you guys got this? Because I need to erase my picture. To put this into perspective, however, the surface area of Earth is, for a sphere, is 4 pi r squared. 4 times pi times 6,400 kilometers squared. I'm just going to punch this because I don't feel like thinking. 6,400 squared times 4 times pi. Wow. 500 million square kilometers. Holy shit. Let me just try that one more time. 4 times pi times 6,400 squared equals. Yeah. 1, 2, 3, 4, 5, 6. So the percentage of the surface area would be 2 million square kilometers over 500 million. Watch these science moves, guys. Watch these science maths moves. Bada bing, bada boom. 2 parts in 500 is 1/250th. Or what would that be as a percent? A hundredth would be 0.1, sorry, 0.01, or 1%. 1/200th would be 0.005, right? Plus
0.0025.
but it's actually 250. So anyways, all right, let's just divide it. 4 times 10 to the minus 3. 0.4%. Even though this area is large, it's still, I think one of the takeaways from this problem is done, by the way, but even in 100 million years, you create what seems like a pretty big territory, maybe like a third of the United States or something, right? But it's still a small percentage of the overall surface area. All right, 2 down, 3 to go. I'm going to erase with everyone's permission. We're moving on to chapter 10 now. Nori, you're next to my box. Do you have the problem? You're kind of working off your phone today. That might be hard for you, huh? Or do you have the problems?
I have the problems, but you won't see me for a second.
All right, that's okay. Well, that'll break our hearts, but we'll listen to you.
Question 51.
Yep.
Magic.
Oh yeah.
Suppose we can magically give Mercury the same atmosphere as Earth, assuming this magical intervention happened only once. Would Mercury be able to keep its new atmosphere? Explain.
Okay, so Mercury has a radius of 2,400 kilometers. Let's imagine we decide to terraform the planet, and we go and we try to add some atmospheric gas to the planet. This is a question that you guys are well positioned to answer, having had this week's lecture. What would happen to a terraformed atmosphere?
Volcanism, lithosphere, atmosphere.
Hold on, Austin. I'm having trouble with your beat poetry there. What are you saying?
Well, I'm saying that one of those 3 words has got to give some direction to the question.
Yeah.
Specifically volcanism, geological structures and features.
Okay, well, tell me about volcanism on Mercury.
Yeah, like I only have the word.
Oh, okay. You're trying though. I noble effort. Jenna, Kim, can you guys tell me about volcanism on Mercury? You guys are usually with me, hanging, talking. Tell me about those legendary volcanoes on Mercury. Maybe we haven't spent enough time looking at pictures of Mercury. Luckily, there's a bunch of images from the Messenger spacecraft. Here's the Messenger spacecraft's picture of Mercury. What are we seeing here?
A lot of impact cratering,
Yeah.
tectonic scarps.
Yeah, we can see. Oh, very good. You can see some of those tectonic scarps. Look at them there and there. Something tectonic happened on Mercury.
Sorry, I had to grab something, but I was going to say that I think that Mercury is too small to really support a ton of geological activity.
Right.
So it wouldn't be able
in this case, we're concerned about the atmosphere. So you are correct, but keep going.
Well, I was going to say it's too small to maintain any kind of serious geological activity, so it would really be able to.
Well, what type of? We don't want to talk about all geology here. What type of geology affects atmospheres?
Well, volcanism, sure. So
And-
it's
and
too
then-
small. It doesn't have enough internal heat to support volcanism.
Yeah.
So the lithosphere will be too thick. So the atmosphere would probably just boil away in the sun.
Right. Okay. So it's actually a complex set of issues here. That's this, but you're hitting on some of them. There are no volcanoes on Mercury, and therefore no atmospheric gas will be replenished. Now, I'd say I don't need volcanoes because I just magically put my atmosphere there with a magical atmosphere machine. But now let's talk about what would happen to that atmosphere. First of all, we got no volcanoes, so you can't add more gas. But then what happens to the gas that you did add?
It would, at least on the side facing the sun, it would probably boil away.
It would achieve, what's the fancy term that we have for when an atmosphere boils away? It would achieve, begins with a T. It's like the thermal escape.
Right. Yeah.
What about other issues besides just, well, Mercury's also small. How does the smallness or size of the planet affect it?
Well, I kind of said this, but it has no internal heat, so it wouldn't.
But not just internal heat. There's another thing the size affects.
Oh.
Look at your notes from today.
Yeah.
Gravity.
And how would that play into it, Jenna?
It would have almost no gravity.
Well, it'll have gravity, but it'll have a lot less than a big planet like Earth's. And that will
wouldn't
make
be
it
able to-
easier for the planets to jump off into space. There's one last component that you haven't thought about. There's another type of escape from a planet. What else would Mercury be suffering from with its lack of magnetic field?
Temperatures or wind erosion?
Wait, I mean wind erosion.
Solar winds.
Solar winds. Could you imagine the flux of solar wind particles on this planet? This thing is being bombarded by high intensity radiation from the sun, particle radiation, that will just knock those gas particles right off. And Mercury lacks a magnetic field, so it has no magnetic bubble. So it's actually a complex problem. No volcanism, small gravity, high daytime temperatures, lack of a magnetic field. Let's get that down. Mercury could not maintain an artificial atmosphere because of several factors. The planet is small and lacks the internal heat needed to support volcanism. Thus, atmospheric gas could not be replenished. Mercury's low surface gravity coupled with high daytime temperatures would encourage gases to thermal escape. Let's underline thermal escape because that's a key concept. And lastly, let's throw in the magnetic field bit. Lastly, without a strong magnetic field, atmospheric gas would be subject to constant harassment from the high flux. Flux just means like number of particles of solar wind ions. This is why when you watch a movie like Total Recall with Arnold Schwarzenegger, when he touches the alien hand at the end of the movie, and it turns out the aliens have just been keeping this ready-made terraformed atmosphere on Mars, even if you pump those gases into Mars's atmosphere, eventually it wouldn't be quite as bad as Mercury. Mars would hold it a little better for a while. But even today, Mars's atmosphere is 1% the density of our own. Even Mars is going through a similar process today of losing its atmosphere. You need to replenish your atmospheres, and you need a magnetic field, and you need the right distance from the sun, and you need the right gravity.
Professor.
Yeah.
What if you also artificially added mass to the planet
yeah.
somehow?
That's the idea, is if you're going to go all out, you've got to take care of those fundamental planetary properties. If we could get Venus a spinning, who knows? Maybe we could create another possibly livable world, although you need time too. But nothing's out of the realm of imagination if you have sufficient operational scale, you know? We're not quite there yet, but it would be cool to see a future world that was, that's for sure. You know, like I love that TV show, The Expanse, that's on Amazon Prime right now. Like they did such a good job with the science of that show. It's a story that takes place across the entire solar system. And many of the bodies we talk about in this class appear in the show. The asteroids Ceres, moons of Jupiter that we're going to talk about next week. And they did pretty good with the science. They did a good imagining how people might adapt to live on Mars in this thinner atmosphere under bubble domes, and how people could potentially adapt to outer space living as that community of miners do out in the asteroid belt. If you haven't seen that show, one of my close friends hates it. He calls it sci-fi C-SPAN. He says it's boring, but I love it. I love that show. I could watch that show. I've watched it twice. It's so good. So check that out.
What's it called, Professor? The
Expanse. It's really good. And if you have an Amazon Prime account, you can just click it and watch it. There's like a few seasons, and I think having taken this class and having spent some time thinking about space, you'll get a kick out of seeing some of the things we've talked about in this class show up in that show. And it's wildly entertaining too. So if you end up liking it, tell me all about it. Okay.
I have a question.
Yes,
the screen on my phone is kind of small. Can you just like tell me the last 3 words that you wrote?
Sure. I'm going to read the last sentence. Lastly, without a strong magnetic field, atmospheric gas would be subject to constant harassment from the high flux, FLUX, of solar wind ions. We cool? I'm racing.
I don't know what you said, Professor. My computer died, but I'll watch the show.
Yeah, watch the show. It's really good. You'll love it. Okay. Kim, can you read us number 63?
It is the cooling clouds of Venus. Table 10.2 shows that Venus's temperature in the absence of the greenhouse effect is lower than Earth's. Even though Venus is closer to the sun, what would Venus's no greenhouse temperature be if its clouds were more transparent, giving a reflectivity the same as Earth's? What would the actual surface temperature be in this case if the greenhouse effect increased the surface temperature by the same number of degrees that it does today?
We've been privy to a sophisticated discussion about this today, and you guys may not remember this, but Earth's global albedo, considering its color, is actually, I think we're going to have to supersede the book here. Earth's global albedo, considering the oceans and the grassland and the continents, according to this slide, is about 31%. So I'm assuming that's the number they want us to use. But what would you guys say would be a more reasonable albedo for the surface of Venus? Ian, we talked about this today, right?
Yeah. I don't know, maybe something closer to the asphalt, the blacktop, since it's dark volcanic rock, but maybe a little bit higher.
Sure. Let's go with the more, let's say 10%. Why don't we not do what the book told us what to do? Because I don't think that's good enough. Unless they mean that there's still some clouds. Why don't we stick with 10%, which might be some dark volcanic rock? So the surface of Venus is black volcanic rock. And we're going to use an albedo of 10% or 0.1. The distance from the sun is is it 6.3 AU? Why can I never remember little things like that? By the way, the table 10.2 that they referred to in the question was the one that we stared at today here, right? Oh, sorry, 0.723 AU. So first, we'll find the no greenhouse temperature. Which is a reference 280 Kelvin times the fourth root of 1 minus 0.1 divided by 0.723 AU squared. Think you guys can punch all that up for me? Where's that glare? Oh, the glare is coming from the computer, actually. Remember, that's a fourth root there, peoples. Nori, you never have your calculator, huh? Oh, holy shit! Nori, this is amazing. This is absolutely amazing. You should.
I was like, I'm gonna forget it today.
You should punch this one up for us, or you might not have. You don't know how to do it because you haven't done that yet.
I'm probably gonna. I don't really know how.
Okay, then why don't you follow after me? Everyone will do it together.
I agree. I don't know how to do this one.
All right. What we could put this in parentheses, or we could just hit equals after we do the top. I'm worried about order of operations issues. So let's do 1 minus 0.1 and hit equals. Notice that I tend to tackle the inside of the root thing first. Now let's divide it by 0.723. We have to square that because of the inverse square law and hit equals. Right now I've got a factor of 1.72. Now we're going to take the fourth root. So we do shift. The arbitrary root key is here. You have to hit shift first. 4 for fourth root, and then equals. And now we're going to multiply that by 280.
Yeah, I remember what button it was, but I was doing the 280 first, and it kept coming out weird.
Can you do that one more time?
Sure.
Please.
Yep.
Thank you.
Yeah, no, I kind of sensed that people were getting lost there. So let me grab my Logitech capture because I was kind of far away too. If with Logitech capture control panel, I'll be able to focus. Just let it load. This thing takes forever. Sorry. It's almost loaded. Come on, baby. Come on, baby. There we go. All right. So I can manually focus. Oh, install later. Oh my God. It asked me if I wanted to update. And as soon as I said install later, it tries to reload the program. Way to go, software engineer. You suck. Okay, let's hear it. There we go. There we go. All right, 35. Now I focused up close. So the trick to remember, Nori, the key moment in this operation is that the fourth root is the same as x to the power of 1/4. So we're going to be using this key when the right time comes. So let's start with the top. Ready? 1 minus 0.1 equals. Every time you get what I get, say yes. Divided by 0.723. We have to square that. Oop. And then equals. All right. Now let's fourth root. Shift arbitrary root 4 equals. And now times 280. So we're left with 320, 321. Let's just do 320 because the third sig fig isn't really relevant. So we get about 320 Kelvin. I should have asked you that. The units are Kelvin. How much Celsius is that? You have to add 273, I think, right? Oh, wait. Yeah. $590 degrees Celsius. That's before the greenhouse effect. Do you guys remember how much temperature change was added by Venus's greenhouse effect? Gotta look at table 10.2.
I didn't have it written down. Yeah, it was on that table, right?
Let's read it together then.
So 513 Celsius degrees.
Yeah, 515.
So plus 500 Celsius degrees of greenhouse brings us to a net temperature of 1090 degrees Celsius. Once again, that's also silly because the clouds that add the greenhouse also add reflectivity. You know what's effed up about greenhouse, about Venus's cloud tops? The carbon dioxide clouds of Venus are highly reflective. They're shiny, reflective, white-yellow clouds, right? Oh, wow, my internet's dragging ass today. I think I've got too many tabs open, that's why.
I was going to say, I think it might be the 30 tabs you have open.
Yeah, I know. I love the damn tabs. Okay. This will improve the quality of the video transfer too. So I should have kept that in check here. Okay. Yeah, there we go.
Looks like my mom's phone, like 40 apps open at once.
Every mom's phone.
Wow, they changed this in the last couple of days. This must be a black and white image. I was hoping to get the color image. Damn. What? Oh, bloody hell. Kind of weird that you'd have Venus planet. A true color image. I just want you guys to remember what the true color image looks like. Come on. There we go. So that's a true color image of Venus right there. Think about it. Those clouds are so reflective with an albedo of 72%. Only 30% of the sunlight actually makes it to the surface. And that 30% sunlight is responsible for 500 Celsius degrees of temperature change. That's pretty wild. Okay, that was the whole problem, right? Who was reading just then? Kim.
Yeah.
Did we miss anything?
Let me go back and look. Let's see.
Austin, why don't you call up them problems since we're graced by your presence today? I'd love to have you read one for old time's sake.
All right, last one. All right, 64.
Yeah, Kim, can I just verify that there was no other ask associated with this?
What would the actual surface temperature be in the case of the greenhouse? In fact, increased the surface temperature by the same number of degrees that it does today. Was the last part.
Right, so we did that, right?
Yep.
We've completed our mission. All right.
Yep.
All right. So Austin, I'm going to erase and then you're going to read me number 64, a final problem.
All right, chapter 10, 64, Mars's elliptical orbit. All right, Mars's distance from the sun varies from 1.3 AU to 1.66 AU. How much does this affect its no greenhouse surface temperature at different times of year? Comment on how this affects Mars's seasons.
Was it 1.3? Was there another digit of significance there?
1.38.
1.38. All right. So once again, we have the sun, and then we have Mars. Getting closer and further from the sun. And I think we're just supposed to calculate the no greenhouse temperature, right? I'm sorry. Wow, I got lost in the sauce. I'm a little smush brain today.
Yeah, how much does this affect its no greenhouse surface temperature at different times of the year?
Let's see if that table has a global albedo for Mars. It looks like it's giving us 25% for its global albedo. So we'll use that value. That sounds right for a red planet, okay? So the albedo is 0.25. Let's calculate it at perihelion at a distance of 1.38 AU. Temperature is 280 Kelvin times the fourth root of 1 minus 0.25 parentheses over 1.38 squared. Why don't you guys see if you learned how to type that in without my help this time? I'd like to have you guys do it. I need some water anyways. Sorry, I've been trying to hold out, but I have this yucky taste in my mouth. What'd you get?
I got around, I got 221.8, so you could say like 220 or 200.
Units?
That would be Kelvin, right?
Kelvin, yeah. What's that in Celsius?
You add 273, right? So that would be 493 Celsius.
Wait, that can't be right.
Or 94. Yeah.
Huh?
I am
493?
not 100% sure what's going on.
Did everyone else get 220 Kelvin?
Oh, for sure. Yeah.
But Mars's surface temperature can't be 400 degrees Celsius, right? That doesn't make any sense. What obvious stupid thing am I doing wrong? We add 273, right?
Is this a scientific breakthrough?
I think so. I think it's time to publish. Letters to Nature, here we come. Did I just?
Are you throwing Ian's name on the paper?
Of course, lead author. All right, how do we do our?
That's big, man. That's gonna look good if you're looking at
Oh,
transfer.
look, it's guys, it's minus 273.
Yeah, okay.
Did we add in the last problem? Did we add 273? Do we need to go back and modify something?
Yes.
Okay, can you guys? I don't have I erased from my dry erase board. What
Alright,
problem
got
was
it
it
up.
where we very foolishly added 273?
We got the no greenhouse temperature for Venus as 320 Kelvin, and we made it 590. So we should instead make it 1.
Can you look, guys? Every time I give instructions without writing it down the board, motherfuckers get lost on me. To put it blunt, okay? So can you all handle this if I just give you a set of instructions? What was the number of that problem, Ian?
63, or are you asking the temperature?
I'll ask that next.
Okay.
Please go to problem 63. When we got our answer in Kelvin, which was in
320 Kelvin.
320 Kelvin, we were supposed to have subtracted 273. To get 47 degrees Celsius, correct?
Yeah.
Then we add that to 500 to get 550 Celsius, which is still extremely hot.
Yeah.
I don't know why.
What was the last part? 47 plus, what was the last number?
500.
500.
Oh, okay.
Oh,
Like 500. Oh, you have to add 500. All right, here we go. Look.
it's 47 plus something equals something. That's what I'm missing.
320 Kelvin minus 273 gives you like minus 47 degrees Celsius. Wait, sorry. Gives you positive 47 degrees Celsius, right?
Yeah.
And then you add 500 degrees Celsius to get, I rounded it to about 550 degrees Celsius. Did you guys follow that? All right. That was really silly. I was thinking upside down with the subtraction and the addition.
It happens.
Yeah, it happens. All right. Whoever that was in the background, I hope that made sense to you this time. Okay, 220. This time we're going to do it right. Minus 273. What does that get?
Negative 52.
Negative 53 is what I got, but whatever. Degrees Celsius. Bam. Okay.
There goes that scientific publication.
Oh, yeah. You ready for the publication, you mean?
Yeah.
Have a breakthrough. All right. So here's our aphelion temperature. A distance of 1.66 AU. Second verse, same as the first. 280 Kelvin over the fourth root of 1 minus the albedo over 1.66 squared. Notice I was able to catch my error by thinking about the problem and realizing that it did not make sense for Mars to have a global surface temperature of 400 degrees Celsius.
Playing critical thinking? Who would have thought?
Yeah.
Do you want me to just say what I got?
Anyone.
I got
Um,
202.
Sure.
That's what Ian got.
Same thing. Yep.
202 Kelvin. And what does that make in Celsius?
-71 Celsius.
Damn, Mars is cold. On the other hand, if Mars had an atmosphere that's 96% CO2, if at one point it was thicker in the past, you could have imagined a greenhouse effect that could have pushed that up over the 0 degree mark so you could have liquid water, right?
Absolutely.
Absolutely. So
Hey,
in a weird
Professor.
way, it's okay that Mars is cold. Mars is actually considered more in the Goldilocks zone than Venus, because with sufficient CO2 in your atmosphere, you could heat the bugger right back up there. If Mars had been the size of Earth, we would probably have alien friends to play with today. That would have been nice. Or to do battle with, or to eat or something, you know?
Well, then the
So
question
you gotta think,
becomes,
guys, if one day we discover intelligent, or let's just say one day we discover alien life out there, what if we find a planet in which the first aliens we encounter look suspiciously like cows? Is it ethical to eat them?
well, I mean, if we're already eating cows, but that would also pose
Yeah,
a
I
really
guess so.
question about
We should actually move all of our factory farming over to that planet, and we'll be good here.
Actually, that's
no,
right.
no,
Yeah.
we keep it on Earth, and then we go over there on the nice.
Oh,
fruit
even
planet.
better.
Oh, I see. Okay. That's how it works in the Expanse. On the Expanse, they've so polluted the Earth that it's actually better to live out in the asteroid belt. Well, better to live on Mars, actually. Mars is like the clean planet.
Well, I was gonna say, if they do look, if life looks anything close to what it looks like on Earth, that poses a really interesting question about, like, so would life always develop along the same paths, the same niches?
Before we answer the last part of this question, to answer that question, you have to go to this cool Wikipedia page called Non-Carbon-Based Forms of Life. It turns out that you cannot just make life out of any old thing you want. Like in The Hitchhiker's Guide to the Galaxy, Douglas Adams proposes that somewhere out in space, there is a hyper-intelligent shade of the color blue. But that's not really doable because you have to like obey the strictures of life, which is maintain homeostasis, reproduce, flagellate yourself around the goo pond or something. I don't remember what all the rules are, but if you have those restrictions, you can make life out of carbon. You can make life out of
Silicon, right?
silicon-based life. You could have like these little silicon robot mosquitoes, some types of nitrogen, and maybe even benzene. But it's actually a surprisingly limited number of things. So probably all life on other planets won't be carbon-based, but there are limited non-carbon-based life is actually just a really cool, now it's been renamed to hypothetical types of biochemistry, but this is just a really damn cool wiki page that I want to share with you guys. Probably no one's going to read it, but just in case, while you're munch your toast and just look at this, munch your toast and read that Wikipedia page because it's pretty funny. It's just interesting. Austin, before we end today, I think there was kind of like a little follow-up at the end question, right? Was there?
Yeah.
Or what did it say?
I have a follow-up question before that follow-up question.
Okay, sure.
What's the point of Kelvin? I forget. I think you've touched on it before, but I forget why it's the same scale, but just a different number.
Because temperature is inherently a positive quantity, right? In fact, you know how I'm going to answer that? With the awesome animated GIF that our fellow students helped me to discover here. If I put the box back on and I remove gravity, and then if I chill this bad boy down to 0 Kelvin, you can see from the animated GIF, Austin, that temperature is an inherently positive quantity because it essentially measures the kinetic energy or speeds of the particles. So once we figured out that the coldest something could be was -273 degrees Celsius, it made more sense to shift the 0 point so that when particles have no motion, when they're stopped, theoretically at 0 Kelvin, that's the baseline, the lowest temperature. And then temperatures only go up from there as we add energy.
Okay.
Does that make sense, or was that too mealy-mouthed? I'm not sure.
Yeah, no, that makes perfect sense. So there can't be any temperature colder than 0 degrees Kelvin?
Nope, there cannot, because that's the hypothetical temperature at which all motion stops. And by the way, the current state of, they call this area of physics low temperature research. Using lasers, we have cooled a bunch of cesium atoms or something down to 1/10 billionth of a degree of absolute zero. But we have never actually gotten there because of the quantum uncertainty and buzziness of the particles. In fact, there's a whole new state of matter called the Bose-Einstein condensate that kicks in under like 3 Kelvin. If you could super cool the wires in your house, you could just flick the switch once and get free electricity for life because resistivity drops. All this weird stuff happens. So there's a lot of cool applications in low temperature physics. What was the follow-up bit to this Mars thing? It was also related to water and temperature, if I remember.
Yeah, the follow-up was comment on how this affects Mars seasons.
Mars seasons. And so they didn't really remember, the cool thing about Mars is the tilt with the variation. So I think what they really wanted to drive at was not so much just, oh wow, distance affects seasons, but a change in, let's see, let's do -53 degrees Celsius minus -73 degrees Celsius. This is a delta T of a delta T of 20 Celsius degrees. Notice I use the temperature differential in the proper way, unlike the book. A change in delta T of 20 Celsius degrees means Mars is, capitalize Mars, Mars is 9% eccentricity, also affects seasons. And the lesson, the cool takeaway lesson from the end of our lecture today was, along with a 25 degree axis tilt, this leads to mild seasons in the northern hemisphere, where most of the liquid water used to flow. I totally killed this marker here. So I was also going to mention that the seasons in the southern hemisphere are harsh, but I guess it's implied by saying that. That's fewer words.
Can you just read the last bit? I can't really see it.
Sure. Along with a 25-degree axis tilt, comma, this leads to mild seasons in the northern hemisphere, comma, where most of the liquid water used to flow. I wanted to say ocean, but I don't know if it was a bona fide ocean or not because I wasn't there. But probably it was. Cool. Another great homework right down the chute. Let's review what was going to happen next week, because next week is our last week of lecture. I want to mention this in the recording in case anyone's actually watching it later on. Next week, we will have Monday's lecture, and we will actually be doing a lab on Monday on the rotation of Jupiter. Wednesday, we will do another lecture and a final homework on the Jovian worlds, and then we will gracefully exit the stage. From the sound of things, most people are going to choose to opt out of taking a final and simply use their midterm grade in its place. Please try to catch up on your work. I have 3 things left to grade, and I can get that done, and I will get that done this weekend. So that means all I'll have to do is grade your final 2 things and you'll be done. But I want to make sure that you guys are aware of what you have and have not turned in. So in my grade center, if I quickly look here with you guys, oh, someone's already pre-done their rotation of Jupiter lab. Weird. Well, let's hope that's actually the right lab submitted there. Probably not. Oh, some people are even pre-gaming it. You could use last year's lecture, I suppose, to pre-game it. And fine, if you want to be that way, then be that way. I don't care. As long as you're doing the work and watching the videos. Okay. Anyways, I have homework 10 and homework 11 to grade. And then for the last week, lab 11 and lab 12. Those will be all I have to grade next week. You see what I'm saying? And then I'll compute your grade, just like you saw me do during the midterm. All right, so keep in touch. And oh, one last thing. It's nice at the end of a course to have the opportunity to evaluate the professor in the course. We're going to do those student ratings of instruction online. I need to activate them, and I have to call Paula, the office guru, to have her tell me how the hell to do that, because I forget every year. But I think when I go into my professor zone on my CCRI, are you going to make me sign in again? I want to just show this to you because you know, I used to hand out the paper evaluations, but I can't do that now. So you guys have to do this on your own, and I encourage you to do it. I go to my for faculty tab. You guys probably go to the for students tab, but somewhere down here, student ratings of instruction. Now I have to figure out how to activate them for this course. I have not done that, but I really should figure that out today, or at least before next week. So all I'm saying is at some point I want you to evaluate the course. Jenna, Kim, I usually see you guys every lecture. Could you please help? Could you please think, if you remember, to ask me? If you have a notebook there, just put a little note to self, ask Brendan about SRIs. And that way I don't forget. All right? Okay, cool. So I'll see you guys on Monday. Have a great weekend. Over and out.